Welcome to OP Studio by OpenPhase Solutions. In this quick tutorial, I will show you how to simulate a solid-state phase transformation in nickel-based superalloys using custom presets. We will go step by step, from setting up the model to running the simulation to visualizing the results, all without writing any custom code. Before we begin the simulation, let us briefly look at nickel-based superalloys and why they are important. These materials are known for their excellent mechanical performance, especially at high temperatures. They offer high creep strength, good oxidation resistance, good corrosion resistance, and strong thermomechanical stability. Because of these properties, nickel-based superalloys are widely used in demanding applications such as aircraft engines, gas turbines, and power plants, where operating temperatures can exceed 800 degrees Celsius. A typical nickel-based superalloy consists of a gamma matrix and gamma prime precipitates. These precipitates play a major role in strengthening the alloy. During cooling, the gamma prime phase precipitates out of the gamma matrix. This is a solid-state phase transformation, where the alloy changes from a single-phase solid solution into a two-phase microstructure. The gamma prime precipitates have a slightly smaller lattice parameter than the gamma matrix. This creates what is known as a negative misfit, which generates a misfit stress field around each precipitate. Nickel-based superalloys also shows cubic elastic anisotropy. In practice, this means the material is elastically softer along the 1-0-0 crystal directions. To reduce its total elastic energy, the system preferentially evolves the precipitate shape along these directions. As a result, the precipitates gradually develop into cuboidal shapes aligned with the 1-0-0 directions. Using OpenPhase, we can simulate this full transformation process. In OpenPhase, we use a custom preset. First, enable thermodynamics and mechanics, since both chemical and elastic effects are involved. Next, we need an OPID file, which is a linearized phase diagram file. To create this file for a binary alloy, you have to start with the phase diagram and draw a horizontal line at the temperature of interest. For example, 1223 Kelvin. At this temperature, identify the intersection points with the phase boundaries. These give the equilibrium compositions in mole fraction. For the gamma prime phase, we assume a stoichiometric composition, so it appears as a vertical line. Now repeat the same step at a nearby temperature, for example 1224 Kelvin. These values are entered into the OPID file and used in the simulation to define the thermodynamic behavior. Now let us create the OPID file. First, we specify the components. Component 0 is aluminum and component 1 is nickel. Next, we define the phases. Phase 0 is gamma, labeled as FCC_L12. Phase 1 is gamma prime, labeled as FCC_L12-2. Then we provide the nominal composition. This is a reference composition in mole fraction, chosen between the equilibrium compositions of gamma and gamma prime. The file follows a specific format. We begin with a EQ_gamma phase name, _gamma prime phase name, followed by a colon. On the next line, we write 2 slashes. Then we define the headers: temperature, entropy of gamma prime, composition of aluminum and gamma, composition of nickel and gamma, composition of aluminum and gamma prime, and composition of nickel and gamma prime. After that, we enter 2 rows of data using the temperatures and compositions obtained from the phase diagram. The entropy of each phase can be obtained from thermocalc or from literature data. The units of entropy are joules per mole Kelvin. The composition is given in mole fraction. Therefore, the sum of aluminum and nickel in the gamma phase must be equal to 1, and the same applies to the gamma prime phase. Finally, we define the diffusion coefficients. This includes aluminum and gamma prime, and nickel and gamma prime phase. Then, we upload the OPID file that was just created in OpenPhase. After that, click Continue, and then click Finish. And here we are greeted by the periodic table. The elements and phases are already selected because of the OPID file. The elements are nickel and aluminum, and the phases are gamma and gamma prime. We set the reference element to nickel, then click Apply and Continue. In runtime control, we define the simulation title. The total number of time steps is set to 10,000, with output to disk and to screen every 100 time steps. The time step can be set as high as 10, provided it satisfies the CFL condition, which depends on the diffusivity and the grid spacing. The number of OpenMP threads is chosen based on the number of processors available on your system. In our case, we select 4 threads. In settings, boundary conditions, and driving force, no changes are required. Finally, in the grid parameters, we set the spacing to 30 nanometers. The simulation box size is set to 100 by 100 by 100 grid points. For interface energies, we use the isotropic model. The interface energy between gamma and gamma prime is 0.05, while the energy between gamma prime and gamma prime is 0.15. This creates a wetting condition that prevents the merging of gamma prime precipitates. For a more detailed description, please refer to the paper linked in the video description. The interface mobility is set to 1 times 10 to the power of minus 17, which is comparable to the diffusivity of the slowest element, rhenium. The temperature is set to 1223 Kelvin. In the Composition tab, we define the initial compositions of aluminum and nickel in the gamma and gamma prime phases. These are given in mole fraction. The composition is chosen such that it corresponds to the equilibrium composition of gamma prime phase, while gamma represents the initial matrix composition across the whole domain. Next, we enable the stoichiometric phase for the gamma prime phase, where the composition of aluminum and nickel remains fixed. For diffusion, we select the extrapolation mode as global. In equilibrium partitioning, we enable partitioning between gamma and gamma prime, and select the two-step model. In the kinetic interface tab, we choose the Arrhenius model and use the same OPID file created earlier. In the thermodynamic interface, we select the linearized phase diagram model. Now, moving to mechanical properties, we open the elasticity tab. Since this is a solid-state phase transformation, we keep the mechanical boundary conditions unchanged. We then define the elastic coefficients for gamma and gamma prime. Finally, we set the transformation stretches, which represent the eigenstrain. If there is no lattice misfit, the diagonal values are set to 1. For gamma prime, which has a negative lattice misfit of about 0.003, the transformation stretch is set to 0.997. For the spectral elasticity solver, no changes are required. Now click Apply and Continue, and proceed to set the initial microstructure condition. Next, in the Microstructure tab, we initialize the microstructure. We start with a single-phase gamma matrix, which is already selected. Then we create a new initialization using quasi-random nuclei. This places small gamma prime nuclei inside the gamma matrix, with a spacing of about 20 grid points. These nuclei act as seeds which will grow during the simulation if sufficient driving force is available. To better understand the quasi-random initialization, you can use the helper application, OPID. Here, open the Initialization Explorer and select quasi-random nuclei. You can control several parameters. Spacing in X and Y defines the distance between nucleation points in each direction. Offset in X and Y determines how far the pattern is shifted from the edges of the domain. Deviation in X and Y controls how much randomness is added around each point. Threshold defines the probability of nucleation. Increasing the threshold reduces the number of nuclei. Finally, changing the seed value produces different random distributions for the same parameters. Now click Apply and Continue. Finally, click Start Simulation. You'll be prompted to save the preset and select a directory where all simulation output data will be stored. Once confirmed, the simulation starts and you can monitor the progress through the output displayed in the panel below. To visualize the results in OP Studio, click on Update Data. If you want the plots to refresh automatically during the simulation, enable Auto Update. Here, we select volume fraction and observe how it evolves over time. You can also view the temperature, which remains constant, and the driving force as it changes during the simulation. To visualize the simulation results, open ParaView. From the VTK directory, load the phase field file and click Apply. Select phase fields and set the representation to surface, then move the time slider to the final step to view the microstructure. Next, go to Filters and select ISO volume. For the input scalars, choose phase fraction of 0. Set the minimum to 0 and the maximum to 0.5, then click Apply. You can switch to solid color to display a uniform color. To visualize stresses, select a field such as von Mises from the dropdown. To better see the microstructure, apply a clip filter. In each direction, set the value to 98 since the total grid size is 100. This trims the outer region and reveals the gamma prime precipitates and the stress distribution between them. You can also visualize stresses in the X direction, Y direction, and Z direction, as well as all other stress components. You can also view pressure, which represents the negative hydrostatic stress. Press play to observe how the pressure evolves over time during the simulation. Next, select von Mises stress and press play again to observe how it evolves over time. These are the final visualization results of the solid-state transformation in nickel-based superalloys. If OP Studio fits your workflow, download the free trial or explore the licensing options on our website. Subscribe to our YouTube channel for more technical tutorials. Thank you for watching.